base it on the soil series that are mapped in the field that you're planning for. And so understanding how that soil survey got made and what it represents is very helpful to you in getting your job done. So let's launch in and start talking about soil survey. What's interesting in this cover picture is that you can see multiple different colors of soil in the same field.
You need to reshare your screen, John. Sorry, you didn't reshare your screen. There we go.
All right. That will help. Okay, maybe I should start again then. All right, so let's talk about soil survey and distribution in the field, because very seldom are farm fields or hay pastures one soil. Most of the time there are multiple different soils, and those soils have different values. And so for your planning, not just for your lime application, but also for your planning on yields and fertilization, you'll want to see how the soils change in the given field. So we'll start by looking at this cover picture, and you'll see that there are multiple different colors of soils in this field. And so therefore, not all parts of the field are going to require the same management or fertility or lime. So we'll talk about variability within the fields, how surveys are made, components of surveys, so that you'll be familiar with the terms. And again, looking at this picture, we see soils that are shallow to rock. We see steep soils that are in pasture but not farmed. We see more level soils in the area to the right that are farmed, but you can see that there's multiple different colors and probably levels of erosion too. The areas that are bright red to the surface have lost all their topsoil, and that topsoil is down in the bottom over to the right. So we got different soils in here that require different management. And so soil A might be that dark soil, soil B might be that white colored soil, and soil C might be the red colored soil in the field. And here we have soil D, which would be, again, shallow, steep, not farmed, but very different if you're doing fertilization on the pasture land. And one of the variables about soils is the depth of bedrock, or the depth of rooting zone. You can see in this construction zone picture that the depth of bedrock, these are called pinnacles because this is limestone in the valley and ridge. And you can see that the depth of bedrock is highly variable. And so, of course, we don't have the same soil. If the depth of bedrock is different, then the soil series will be different. The rooting depth will be different, and therefore the potential yield will be different. Okay, so when we have relationships between soils that occur side by side in a field, we call that relationship catena, and catena means chain. And so this means that these soils are formed next to each other, basically. But they differ in one aspect. Maybe it's the depth to water table. Maybe it's the depth of bedrock. Maybe it's the surface texture. There's something about them that's distinctly different, even though they're very closely related. You might call them cousins. All right, so here's a diagram of a relationship between soils that occur close together in the Piedmont. And so in certain counties, in certain parts of the county, if you have sisal soil on a summit, you can expect to find ashlar on the side slope. You might find worsham down in the floodplain. And you can see by the drawing that there's a difference. Ashlar and Abel are shallower to bedrock than sisal is. Okay. A soil series is a soil that differs from all other soils in some important classification or management property. So if it's classification, that's a very, excuse me, very complex set of names that most of you don't need to be familiar with. But for soil scientists, we use classification, soil taxonomy, to help us know when soils should be separated from each other. In other words, when they should not be grouped into the same soil series. But there's also things that are not found in soil taxonomy that split soil series. And like I mentioned a few of them before, whether it's flooded or not flooded. You wouldn't want to put both of those flooded and non-flooded soils together into the same map unit. Depth to bedrock, type parent material. Excuse me. So some examples of some soils that are found all over the state: Cecil, Pacolet, Norfolk, Roanoke, Rains, Emporia, Frederick, Glenelg, Grosclose. Those are some of the most extensive series in Virginia. Here's the information about a soil series, and it's called the official series description. It tells you a little bit about the soil in a general description that's in the header. Then it gives you the taxonomy, and then it describes a soil that is very representative of that soil series. It also tells you, and it does it by layer by layer. It also tells you where that soil occurs, both physiographically and on the landscape. And then it tells you what other soils are usually found in the catena next to that soil. And so by learning and studying about the different soils in your work area, you can become very familiar with their potential productivity, with their clay type, drainage class, and you can pretty much commit this to memory. Here's a picture of the state soil of Virginia, and it is called the Pamunkey series, and it is found along the floodplains of the Pamunkey and the James River are two of the big ones. And I think either one of the other rivers in the area, they're found on river terraces. And the reason it's the state soil is because the James River drains all of the physiographic provinces, either in Virginia or West Virginia. And so that pulls in kind of, you might say, a mixture of soils from all over the state, dumps them out in the terraces of the James River. And then so that they thought that was the best representation. It's also one of the most productive soils in Virginia. It's loamy. It's well drained. It has very high water holding capacity. It has no restrictions to rooting depth. And it starts out with fairly decent pH levels and fertility, natural fertility. So it's no wonder that it sets records for yields in different categories every year. Okay, so learn about the soil series in your area. You can use an online app. It's also available for free on your phone. It's called Soil Web. And it's got a nice little feature because it's got a GPS tracker in it. And you can simply click on the map wherever you're standing, and it will tell you what soil is mapped right where you're standing. You can be driving down the road. Your partner can be driving down the road, or your vehicle can be driving down the road. But if you're in the passenger seat, you can be keeping track of what the soils are as you're driving, or someone else is driving, Okay. You use that soil series name to look up information in values. It tells you not just the name of the soil series, it gives you that link to that description that I just showed you. And it also gives you a map unit symbol, which I think is useful in values as well. Okay. If you don't use Soil Web, if you just want to go to the internet, you just type in a search, put in the name of any soil series, and put soil series after it, and you'll get that information, that official description that I showed you just a minute ago. You can also use Web Soil Survey to learn about your soils in your area or in the particular field where you're going to be planting. So Soil Web is very handy for getting quick information about the soil where you're standing. Web Soil Survey is useful for producing maps that you can use in your planning and also calculates acreage for you. So those are very handy tools. This is a set of instructions on how to use or how a soil survey was made. And it helps you to understand, if you know how something was made, how to use it. So what the procedure was many years ago is we would take aerial photographs, pencils, erasers, and black ink pens, India ink pens. We would go to the field. We would identify where we were standing. We would dig a hole, and we would put a symbol on the map indicating what soil we found. Then we'd move to a different part of the field, usually in a different location. On average, you dug one hole every 4 to 20 acres. And you projected what the soil type was between where you dug holes. So you might, the first day, you might go out, you might dig a bunch of holes, develop the relationships between the soil and the landscape position. And after that, you just dig one hole per landscape position, and then you'd project the lines from there. So that's why it's not always perfectly accurate. So keep in mind that if you're dealing with a field that's only 5 acres in size, and they might have only dug one hole every 10 acres, they might not have dug a single hole in the field that you're standing in. So don't expect it to be perfect. Also realize that a line on a map of 1 to 24,000 represents a 40-foot wide swath on the soil, on the ground. So, if you're right next to the edge of a line on a map, it's probably not going to be extremely accurate. You want to draw the map unit polygons. They were drawn at a minimum of 4 to 8 acres. And so that means that if they saw something that was really important, like a sinkhole, but that sinkhole was only 1/4 of an acre in size, or 1/8 or 1/16, but they thought it was important, they would put a symbol on the map to indicate what was found there. But they weren't able to draw a line around it because of just the physical limitations. All right. Eventually, after mapping for months in an area, they would develop concepts of what soils were found in what positions, and it would draw what's called block diagrams. You can look these up for every county in the United States. Block diagram is what they're called. And like this one, for example, shows the relationship between different parent materials, different landscape positions, and different soil series. So it teaches you a lot. And then in this one, they actually drew a little sketch of each of the different soils and what they look like. So here's where they might have dug holes where these orange areas are popping up. And after doing that, then they would put together relationships and then project the lines away from that. Not possible to dig a hole in every single soil. Okay, so a soil map unit would delineate areas dominated by one or two or even three kinds of soils. And so in farm fields, we love it when the soil is really uniform and we can just name one soil, like, let's say, Packlet. If the whole field was Packlet, that makes it easy. But that's not always the case. Sometimes two soils are found alternating side by side on a regular repeating pattern, but they're never big enough to map out by themselves. So they're always mapped as a complex because it's a complex unit. It's not a simple unit. All right. So when the map unit is drawn out, it's a line on the map that indicates a landscape position, and it names the dominant 1 to 3 soils in it. It tells what the average slope is, and it tells whether the area is flooded or not, and it tells you what the surface texture is of that dominant soil. Well, here's a picture of a consociation. This is where we might expect to just find one soil, and these areas are very uniform. Oftentimes they're alluvium deposits. And here, this example, it says, is gross close sandy loam, 2 to 7% slopes in this area. That's what you might find on the soil map. Here's what a complex would look like. In this area, you can see that this soil changes every 10 feet. There's no way in the world that you could map out every 10 feet. So, and there's no indication at the surface that they're different. So what you have to do is you calculate what the percentage of each of these two dominant soils is and report that. So when you're doing your values makeup, if you have a map unit that is 40% gross close and 30% Frederick, then you know that you can calculate how much of that field is each of those soil types if they have different values. Okay, there are other map units components that are called inclusions. So if I had 40% of one soil and 35% of the other, that means there's 25% of the area that has to be other soils. And so those soils are named in the soil survey. They may be important, especially if they're things like rock outcrop or sinkholes. And this is a list of the symbols that are used to indicate different things on soil maps, and it's standardized all over the United States. This is what the published soil surveys used to look like before they all became digitized, and now they're all electronic, either PDF copy. All of the printed maps are now PDF copies, but the maps have all been digitized, and now they're all electronic as well. If you're using any type of GIS or geography-based software. Okay. Again, I told you about Soil Web and Web Soil Survey, different purposes, different uses, but the same information. It's just how that information is presented to you. Most people find Soil Web easier to use until it comes time to make a map. And then Web Soil Survey is the one. I have listed on here a set of instructions on how to use it in case you're not familiar with that. For Soil Web, it comes up and you simply click with your finger or a mouse inside one of these map unit polygons, and it tells you what soils are in there, and everything is linked. So the name of the soil is linked. You click on that and it brings up the official description. It even, in Soil Web, even brings up a small sketch of what the soil looks like in real color. Okay, Web Soil Survey is more complex, but again, it has its uses. You can produce reports on it. So here is a list of the instructions on how to use it. This is the advantage of web soil survey is you can draw an area of interest, which is this white line, which I'm assuming is somebody's property lines. And if you're trying to calculate the area within that area, it will tell you. It will calculate and do all the geography, all the mathematics for you. So it comes up with the information on the different map units, the percentage, and the total acres.
Hi, John. Someone asked if the web soil survey is an app. I don't think so. That's still you have to go to the website for the soil survey.
Right. They have not made that for the phone. So if you're using your phone or a tablet, iPad Pro or anything like that out in the field, you'll need to use SoilWeb. What I would do is I would go to Web Soil Survey in the office, and I would either get a screenshot of the map, or I would, I guess, print it and then take it with me to the field. And then I'd use SoilWeb when I was out in the field. And then I'd come back to the office if I made any corrections to the map and do all my calculations.
Thanks. I think that was all the questions so far.
Okay. All right. Well, that's my presentation on soil survey. It's again, you'll need that information to use values and to calculate the percentage of the fields for any of your mathematic rates for total amount of fertilizer to buy and everything like that.
Yep, which we will talk about this afternoon. And if you stick around for plan writing next week ad nauseum, we will talk about those calculations. Be prepared for math on math next week for those of you returning. But thank you so much for your soil expertise this morning and afternoon. Always appreciate everything that you do for us to help us get this background in nutrient management set up for soils. It's incredibly important. All we do is related back to soils. So yeah, if anyone has any questions right now, ask away. If not, thank you for your time this morning, and we will see you. Well, I'll see you in this summer, but hopefully maybe before. You never know.
You're right. Okay. Take care. Thank you.
All right. So now we're going to switch gears a little bit into liming. So normally our schedule would be we talk about soil fertility this afternoon, but we're going to hear about that tomorrow afternoon. So we're going to switch things around, and we're going to start talking about lime. And then that's going to be, I'm looking for my agenda. I have too many things open. We're going to talk about Lyme for the next half an hour or so, and then Dr. Olga Walsh will be joining us to talk about crop production and economics, and then more about the values, which is Virginia Agriculture Land Use Evaluation System. For those of you who want to know what the exciting acronyms are, forgot it already, because we use a lot of acronyms. But yeah, that's basically talking about how you can determine the yield of a particular soil in Virginia. I'm going to share my screen, and I'm going to pull up Dr. Walsh's presentation since she is in another meeting. I'm going to do my best to, moderate this as we go. So if anyone has any questions, I have the chat open. You can also kind of put that hand up in the corner. And I should be able to see it. Let's see. Slideshow from beginning. That is not right. Try this again. Oh, come on. Please. There you go. All right. Can you all see now that it is the presentation when I move slides? Did it change for you all? Oof. Someone say yes to me right now. I can't see anything. There we go.
Yes.
Okay, good. Thank you. Thank you. All right. So we are going to talk about the acidic soils of Virginia, which is actually really good timing for this presentation because in the second to last one, or the last one before lunch, Dr. Galbraith talked a whole lot about how important Lyme is, and it truly is. And one of you all mentioned in a question at the end that, would it be considered a waste of resources to apply nutrients without your line being correct? And, it's yes, basically, the soil is not able to take it up at a certain rate. Whenever your pH gets too low, nutrients that you don't want available do become available, which can lead to toxicity and other negative impacts of it. So we're going to talk a lot a bit about Lyme. It tends to be kind of brushed over in that, oh, you just need to lime your soil, whatever. It's the last thing on the list, but it's pretty far up there. So low pH in the soil limits many Virginia farmers because we tend to have a naturally acidic soil, 3.8 to 7.5. The climate and our clay and soil types tend to favor acidic soil. And that might seem tricky. And yes, we don't want too low of a pH of soil, but I personally would rather have to work with bringing up a soil's pH than bringing it down. The higher the higher you get on the alkalinity or the basic side, the tougher it is. Crops really do not like that. And if you remember back to Dr. Galbraith's one slide, he had in there that the pH of lemons and vinegar was 2, whereas lye and bleach was, I think it was 12. I'd much rather hold vinegar in my hand than bleach. So I think it's much easier to work with an acidic soil than it is a basic soil, alkaline. You see a lot of the alkaline soils out west where you have a lot of the calcium kind of based bedrock deserts type out there. So thankfully that is not one of our issues. But soil acidity can be directly toxic to plants. It reduces the efficiency of nutrient utilization, P, K, and N, but a lot of times phosphorus can be heavily limited. Proper management of soil acidity is foundational in building up your fertility. So the basis of it is how much acidity or alkalinity is there in the soil. pH indicates the concentration of hydrogen ions to hydroxide ions. So that's H plus and OH minus. We have a nice little chart here showing you kind of on the red, orange, yellow side acidity, the blue, purple side alkalinity, pH of 7, is neutral. Generally 6.8 to 7.2, I think, is near neutral. Anything below 7 is acidic. Anything above 7 is alkaline or basic. There's so many different terms for one thing. And it's a logarithmic scale. So that doesn't mean it just changes going from, a 6 to a 7. It's a tiny little change. It's a significant change in the chemical environment and biological processes. So basically, when you're looking at a logarithmic scale, it's doing a complex expression, taking 1.2 times 10 to the negative 4th and turning that into a single number. So logarithmic scales are big jumps up from one number to the next. Change of 1 pH represents a 10-fold change in hydrogen ions, which is the acidity, or the hydrox ion concentration, which is the alkalinity. So soil with a pH of 5 is 10 times more acidic than a soil with a pH of 6. and it is 100 times more acidic than a pH soil of 7. Optimal pH really depends on what crop you're growing, but for a majority of Virginia's agronomic crops, we aim for 6.2 as a sweet spot. For your major row crops, most grasses, there are a few outliers. 6.8 is what you're looking for generally with alfalfa. And if you're growing a tobacco or anything like that, it's 5.8, like Dr. Galbraith mentioned this morning. Azaleas, blueberries, they really like low pHs, more towards the low 5 or, excuse me, high 4 scale. But generally, you're not doing large scale decreases of pH unless you're growing blueberries for production. But for the main part, you want to aim for a 6.2 in your pH for most of Virginia's agronomic crops. 6.5, a lot of times you'll see is optimal for more of your vegetable crops. A lot of the tomatoes and whatnot like that 6.5, but 6.2 gets you for most of your corn, your wheat, your beans, etc. This chart is also, I believe, in your Mid-Atlantic Nutrient Management Handbook. And it's pretty handy because it will show you what nutrients are most available at what pH. So when we're looking at this chart here, you can see you have your majors. Can you see my arrow? I hope you can. Your nitrogen, you're looking at it being most available between, I'd say, starting at 5.5, but really 6 to 7.5. It's the most available, becoming less available the higher you get. You can see your calcium, obviously, is going to be more in the neutral. Your phosphorus is, again, you're looking at this kind of 6.2 to 6.5. It's what we're aiming for because that's where soils are naturally going to hold the pH easier here. Your potassium as well. And down here, you'll see the lower the pH, your iron, your manganese, and your boron become much more available, which can lead to some issues, especially with aluminum and magnesium. They can cause toxicity issues. So you want to make sure you're keeping your pH and potentially your grasses in that circumstance on more towards the neutral side. pH also helps set what your microbiota are doing. They too have an optimal pH range. And so we don't talk a huge amount about soil microbial health here because we're more looking at kind of nutrients, but it is all related. And the more microbes you have in your soil, generally, the more productive a soil it is. So for your microorganisms with your bacteria, you're looking at between 5 and 9, with an optimum being 7. And kind of down the line. Fungi is a little bit of an outlier with wanting a lower pH, but that could also have to deal with the type of nutrients that they're breaking down. Like Dr. Galbraith mentioned, they are the ones that break down tree lignins. So depending on the tree type, especially if you pines, they tend to be a more acidic soil creating environment as well. Very acidic or very alkaline soils will lead to poor microbial health, which will slow down or stop the general mineralization of the organic matter, which is what's added into that topsoil to help add it's the humus, what you're looking at. Low pH inhibits nitrification and nitrogen fixation, which are two very important things when it comes to the nitrogen cycle and relating to how that works through nutrient cycling through the soil. There is a pretty handy chart. I think it's page, they're 60 or 70, I can't remember, in the Mid-Atlantic Nutrient Management Handbook that will show you the nitrogen cycle. And it really does show how all of this nitrification and fixation help cycle the nutrients through the cycle and how inhibiting that can really slow down how much nitrogen and nutrients are available in your soil. So the importance of soil pH, either having low or excessive, Deficiencies in many of the nutrients, decline of microbial activity, which leads to lower crop yields or issues within that system. What causes soil acidity? There's a whole bunch of different factors, just being in the type of clay that we are, but rainfall leaches basic elements. You've your calcium, your magnesium, your sodium, your potassium. Having acidic parent material, such as granite, is more acidic than shale or sandstone. Having organic matter, lots of it, can decay and produces hydrogen ions. And harvesting high yielding crops can also take a lot of that off of the field. Not only you're taking away the nutrients, you could be taking away some of the higher pH as well. So here is a, I guess, display chart. Can't think of the right word right now, but it's showing the exchanging of hydrogen in the cation exchange capacity. So Dr. Galbraith really went through this too and didn't realize how well these two presentations lined up until we were kind of listening to them back to back. But basically, with the CEC, as he was saying, depending on the type of clay you have, it's going to vastly influence how much cation activity is available in that soil. So a soil that is on the lower side of the pH, if you remember back to his presentation, the humus, when you are below the optimum pH, you were looking at even, 100 versus 180 when you're at your optimum pH level. And so that cation exchange capacity is what helps keep the nutrients in the soil available for the plants. So if your pH is not quite where it should be, it could be vastly influencing the exchange capacity of your nutrients. So a variety of agriculture practices can also decrease the pH. Applying ammonium-based fertilizers, urea, sulfur, ferrous sulfate, those are all going to add elements that will reduce the pH. Irrigating with acidifying fertilizers or using acidifying residues such as moss, pine needles, or sawdust. It's always recommended that if you are going to do any kind of mulching with that, even, if it's not mulching for large scale farming, don't mulch your backyard with pine needles unless you have a lot of pine trees, or you're going to see acidification happen. Increasing soil organic matter can increase the buffer capacity, which allows more wiggle room, I guess, before your pH would be affected. So the more organic matter you have, the more potentially stable your pH could be. So how do we go about increasing this low pH that we naturally have in Virginia? We can do it through liming, additions of organic residues in basic cations, or crop rotations to interrupt the acidifying effects of legumes. So what is lime? The chemical definition of lime is calcium oxide, that's CaO. In agriculture, lime is defined as either having calcium or calcium magnesium compounds. It's capable of reducing the effects of acidity and neutralizes that soil acidity and raises the soil pH. Where does it come from? It is derived from limestone, which is calcium carbonate, CaCO3, which is a sedimentary rock formed millions of years ago, and it's accumulated through shell, coral, algae, or ocean debris. So if you have a driveway that you put a lot of shell down in, I know a lot of oyster shells are around here, you could have a potential great source of lime just sitting in your driveway. So lime is mined, crushed, and then sized, and then put in kilns at 2000 degrees Fahrenheit, which changes calcium carbonate into CaO. And we're going to talk in a little bit. You can see the picture here. The top picture would be considered kind of a chunkier lime, which there are pros and cons to both, where the bottom picture is a more fine ground mesh. And so depending on what kind of lime you get, it's going to react into the environment differently. So liming reduces soil acidity through the calcium ion from which replaces two hydrogen ions, excuse me, in that cation exchange capacity. And so the hydrogen combines to form water with OH, and the soil pH increases because the acidity source, which is that hydrogen, has been reduced, turned into water. Here is the chemical equation for neutralizing acidity with lime. You can see here, we're putting our calcium carbonate with water. This calcium displaces the aluminum and hydrogen from the clay, breaks down to carbon dioxide and water, and then that combines with the H plus and is released from the clay or from the aluminum OH to form water. And so how it reacts in soil, in moist soil, calcium carbonate from limestone separates or ionizes into calcium and carbonate ions, and those bind into the soil constituent. Excess hydrogen ions caused by the soil being acidic react with this carbonate to form water and carbon dioxide. Carbon dioxide is released into the air, and the hydrogen ions that were contributing to soil acidity are chemically bound in soil water. So we're going to talk next about the different types of liming sources, because you don't have to go out and just buy, limestone to, increase your pH. There's several different varieties, and depending on the particle size, it's going to influence the neutralizing power. So here we have a lime particle size chart. And so here it's saying this 10 mesh is making it through you basically get a screen. And these mesh sizes are, I cannot think off the top of my head what exactly the mesh is, but it's depending, I think it's 10 particles making it through the mesh versus a number. This is 1/8 particle size, 3/16, 1/4, 1/2, 3/4 inch. Obviously, the bigger it is, the chunkier it's going to be, the longer this is going to take to break down. This fine ground 200 mesh, which looks pretty much like sand, will react very quickly within the soil. But there's going to be a flip side to that, that unless you put this 200 mesh, you incorporate it into the soil, you're potentially, if you put it down and it's a slightly breezy day, this 200 mesh, it might end up, liming your neighbor's yard versus your yard or farm field if the wind just picks it up and blows it unless you incorporate it. This 3/4 or even down to, 3/16 or so might take a significantly longer time to break down, but it will stay where you put it. So there are pros and cons to both having fine ground or kind of more cobbly. The finer the grind, the more surface area, which makes it more effective. These are standard size sieve meshes. It's going to be labeled on the bag what that sieve is, that mesh is. So here it is. Good thing I didn't have to remember it. So for ground limestone, you have a mesh of that 20 mesh. Guaranteed to pass through is 90% of that material, 60 mesh, 50%, 130%. That's ground. So that's kind of two different methods. You have grinding and you pulverizing, and it's going to create different standards. You can see pulverized mesh, you're still going to get a higher passing rate even at 100. All liming material must be approved and registered for sale. So if you're buying it, it has to be approved for VA Agriculture Limestone Liming Materials Law. Say that once fast. And each package / lot sold must have the brand named and the guaranteed analysis of it. Much like your fertilizer, if you go to purchase it, you're going to get an analysis of that as well. Analysis must indicate if it's burned or unburned, the percent calcium carbonate, manganese carbonate, Ca, and MgO, and the percent ground to a certain mesh size. So you're going to get your full workup of information. We have a scale here which shows the neutralizing power of mesh. So we have our pH running from 4.5 to 7, and then you have your months of application. So 6, 12, and year and a half. If you have a 4 to 8 mesh after, 6 months, you're seeing the pH not really doing a whole lot. It starts here and it'll just go down and kind of plateau further out. If you have 8 to 20% mesh, you're going to see a little dip there. And then at about, I guess it looks like 9 months, you'll start to see the pH rise. For the 40 to 50 and 80 to 100, you're going to see that steeper rise within, 6 months of that application. You'll see significant changes to the pH. So it's faster reacting the more the grind is. This is looking like it'll eventually start to increase down here at 4 to 8, but you're going to be a year and a half out. And if you start at a much lower pH, it's going to take a lot longer to increase that pH. Now here's something that can be a little tricky. So we talked about the cation exchange capacity, which is CEC. Now we have the CCE, not to be confused with that, but this is a calcium carbonate equivalency, because who doesn't need enough acronyms that are almost exactly the same but mean totally different things in your life? So calcium carbonate is set to 100, and all other materials are compared to that value. So if we are comparing calcium carbonate to ground limestone, you're going to see about 85% of that CCE. Burnt or burned limestone, 140%. So it's a greater percentage than your calcium carbonate. And so a lot of times when we make recommendations for lime, you're going to be making it based off of this calcium carbonate. So if we say we need 1 ton of this to increase it, you would need less than a ton if you're working with burnt limestone, potentially more if you're working with ground limestone. Hydrated lime, about the same, maybe a little bit more, and shells are 85%, which would be less, meaning you need more material to bring that pH up. So the CCE is acid neutralizing value of a lime material relative to pure calcium carbonate. That's your 100. Most materials are between 85 to 107, but you can see a variance. Some materials are much greater. So there's a couple of different things that go into the effectiveness of this. You're going to look at your CCE, your articulate/mesh size, the purity, and the chemical composition, which makes up the ag lime effectiveness. Here's an equation that probably don't really have to do, because we have a chart that if you're taking this for, if you're taking this class for the exam, we'll go over next week on how to do this calcium equivalent chart. We have a nice little chart that you just look at, but if you wanted to do it the old-fashioned way, you can look at effective neutralizing value, where A is the percent passing of a 20 mesh sieve minus the percent weight of a 60 mesh sieve times 0.4, and you'll add that to B, which is percent weight of 60 and percent minus percent weight of 100 times 0.8, and your C, percent weight of 100 times 0.1, times your CCE, which is your calcium carbonate equivalent, divided by 100, and that will tell you your ENV, but it will also generally be listed for you. And here's a really nice chart that you don't really have to, the chart is good. Look, remember the chart, but the equation, not so much. You can see some of these are your more popular ones. You have your calcium carbonate 1:1, magnesium carbonate 84, molecular weight, neutralizing value of 119, so a little greater. CaOH2, which is even greater, so about 1 1/3, and then CaO, which is 178, neutralizing to 100. So it's going up as you increase. They're increasing as you go through these equation or formulas. Here are some of the most popular. You have calcite, dolomitic lime, burn lime, hydrated, and marl. What their CCE is. With your calcite, you're mainly looking at calcium being supplied. It's about 1:1, 100 CCE. Your dolomitic lime, a little bit more, but it supplies calcium and magnesium. This is important for the sandy soils where magnesium can be an issue. Burn lime, this is that CaO. It's going to be significantly higher supplying rate because it absorbs H2O faster, and you'll just get more of your neutralizing effect there. So you need less of this material compared to calcite. You have your hydrated lime, which is CaOH2, which acts quickly but can be caustic. And then you have your marl, which is on the left side, 70 to 90, and it tends to be more of a collection of different things, unconsolidated, also your shells. Factors to consider when selecting a lime material: what's available. That can drive a really big portion of the market. So if you are a plan writer, it's best to check with the farmer to see what they can actually get available, and then you can start helping them make actual lime recommendations. Because if the lab tells you, you need 2 tons of lime, but they only have the availability to get marl, maybe you'd want to help them do that conversion of how much of that you'd actually need to get that neutralizing effect. You also go time between liming and planting. It's always asked, what's the best season? I've been told that fall is a good season because that lets you prep up for planting the next spring. But honestly, whenever you can get it available, when it's available, that's the best season, because you're going to need it at some point. Whenever you can get it, whenever you can put it down, even if it doesn't help your crop tomorrow, it's going to help your next season's crop, etc. How low is the pH? Do you need magnesium? What's the value of the crop, and what's the intensity of the cropping? All those things you can look at and have the discussion to see what would be best for that particular situation. So what's the impact of moisture on lime? Outside storage and weather would lead to a higher moisture content, which could potentially reduce the lime's effectiveness. If you're going to store it out in, the middle of the field somewhere and not apply it immediately, and it rains a whole lot on it, you could be essentially reducing the effectiveness of it. To standardize the value of a ton of lime, it's best, the results of the lime are usually reported on a dry basis, and lime moisture may vary from 3 to 10%. They adjust the moisture content based on what's being applied. Oops. Go. Lime application timing. Generally, you're looking at 6 months out, depending on what kind of liming material you have. It could be significantly more than 6 months if you have something that is less pure lime or a much chunkier grind. It depends on how complete the reaction with the soil is. Ag lime meetings VA specifications, they immediately reacts with the soil acidity, and it produces a crop response when being planted. So you're looking at a faster application if we're following the specifics of Virginia law. Most soils require lime every 3 to 5 years. It really depends on the soil type. If you have a clay soil, you might need to apply more lime in the beginning, but once you get your pH up to where you want it, it will hold it there much longer than a sandy soil, because a sandy soil is just not going to be able to hold on to those nutrients like it does. It'll leach through profile for a variety of reasons that Dr. Galbraith talked about this morning. So it really depends on it, what type of soil you're looking at, what type of lime material you're looking at, what the weather's been doing. So there's a whole bunch of different factors, what kind of incorporation you're doing. And ideally, if you have a good quality lime, you can see a pH adjustment in a month and a half to 2 months, but that would depend on a lot of factors, and other information. So in the standards and criteria, which if you're joining us next week for plan writing, we'll talk about Lyme. It's on pages 43 to 45. We talk a bit about Lyme, what's standard crops need in Virginia, which is a 6.2, our CCE percent, and how to do applications based on SMP buffers and Malic 1. We'll make those recommendations. And so how we recommend them in Virginia is if you're doing 2 tons or less per acre, add the entire rate to the soil in a single application, preferred if it's incorporated. If you're recommending 2 tons or more, or if you're recommending more than 2 tons, so say it's 4 tons, apply 50-50 rate. So don't put all 4 tons down at once. Do 2 tons, disc plow under, and then apply the 50% remaining. Maybe not back to back in a little bit of a window, just to give that material time to incorporate into the soil. And if you're doing a no-till, frequent small applications are beneficial compared to a big heavy load, just because you can't incorporate it into the soil. Like I was saying a few moments ago, sandy soils, you're going to see lower Lyme requirements, fast reaction times, but you're going to need more frequent applications just because the soil is not going to hold on to those nutrients. Silty soils are going to need higher Lyme requirements. You're going to see a little bit of a slower reaction, but less frequent, and that's only going to increase as you get into the more clayey soils. So you can see here you have your sandy loam versus your silt loam, where you need 1.5 tons to increase your pH here versus 2.5, but this 2.5 will significantly remain much longer than the sandy soils. And that was all for Lyme today. Any questions? I know we maintaining a healthy farm field. Not seeing any burning questions, and I think I just let Dr. Walsh in a few seconds ago. Whenever you're ready to jump in, we are ready for you. I'm trying to find my agenda again. Because yeah, it looks like we have about half an hour of crop production.
Okay, yeah. Can you hear me okay?
Yes. How are you?
Great, I'm doing great. Thank you so much for helping.
Oh, no problem. Happy to jump in.
scheduling.
Not as good at the line, but it's an important one. So hopefully everyone held in there with me. And if we have any questions, please feel free to ask me or Dr. Walsh on the excitement of Lyme. But otherwise, I don't see any questions. So we'll just jump right into it. And you're good to go. Got the right screen and everything.
Okay. Just double checking that I have my notes. Okay. Okay. Hi, everybody. I know it's been a long day. Let's continue. I want to talk to you today about the crop production. And this is going to be with some examples that relate to Virginia, of course, and the crops that I'm working with. It's much easier for me to relate, which is grain crops. I'm the grain crops extension specialist. I'm going to also get away from the camera so I don't distract myself. Okay, so yeah, so I'll talk today about some of the key aspects of crop production, and the focus primarily will be on nutrient management, since this is my expertise, but also having some more additional information from other specialists. And the focus is basically on optimizing yields for grain crops such as wheat. And I have a couple of examples on that. So to start is, I just want to pose a question for you. In your mind, what do you think that what drives the emergence and the growth of most plants? So first of all, the crops are, they are plants, right? So what does affect and what does hinder it? What does promote plant growth? And it is number one is definitely temperature. So of course, this is biological systems. They are very complicated. Most of us who study plants and soils, we actually realize that the more we learn, the less we know, because there's a lot of interactions that we are aware of and we cannot necessarily explain them. But a lot of times we're not even aware of some of the implications of different interactions that are happening with plants. However, number one, I would say, is kind of a consensus that air temperatures, soil temperatures is definitely number one in terms of plant emergence and crop growth. And this is why the GDD, or growing degree days, is discussed a lot from the point of view of metrics. And this metric especially works well in climates such as we have here in Virginia that cause plants to go dormant during winter. And basically, it helps us to understand and describe what plants are experiencing during their growth at a particular location, which is important because even across the state lines and within a state and even within a farm, but at different fields, we can technically say that these are different locations because they may experience different temperatures, and even temperature may be affected by management. For example, if it's a no-till or tillage systems, so all sorts of things affected, and the location of your crop planting within the field may be affected. So growing degree days helps us to standardize this. And it's basically GDD is a value that is obtained as a sum of mean daily air temperatures throughout the growing season. So this is a cumulative temperature. So whether these temperatures are above a plant-specific threshold. And then this threshold relates to the fact that a plant will only become physiologically active after it receives sufficient number of heat units, or sufficient heat. So growing degree days to think about is basically a sum of mean daily air temperatures, and this is a plant-specific threshold of sufficient heat units, and that indicates the days when plants or crop was physiologically active. It's easy from the point of view of, let's say, humans. It's easy for us to say whether it's cold or hot, although it's relative. But we can just look at the thermometer and say it's cold outside, or we can kind of look inwards, I guess, and say whether I'm cold or hot at this point in time. However, when we're evaluating plants in the field, and definitely in different fields, that's much more difficult, right? So that is why we're using these growing degree days. So for example, a corn plant begins to grow and develop actively at temperatures of about 50 degrees. So plants grow much faster as temperature increases. However, there is a threshold of about 86 degrees where that development and growth actually stops, or it hinders or slows down drastically, because at around those temperatures now we're experiencing, our plant experiences heat stress or drought stress, if there is also water limitations. So that's why the most common method involves calculating growing degree days. Like I said, sometimes it's also called the heat units. And the number of GDD for a date is calculated by finding the day's average temperature, which is basically a maximum plus minimum divided by 2, and then subtracting the the growth threshold, which in this case is 50. And as far as I understand, for most plants, it is 50 degrees. So here's the basic formula that I just talked about. So it's basically a difference between the average temperature during a day and that 50 degrees threshold. And so for most crops, the upper limits are within high 80s or 90s, and then the lower degree, the lower limit is 50. So let's imagine that this is our day 1, and our crop experiencing maximum temperature that day of 78 and minimum of 62. Plugging in the numbers into our GDD formula, we discovered that this day provided our crop 20 heat units. Then the second day, same thing, different growing environment, happens every single day. Temperatures vary greatly. And so the day 2, we have only 3 heat units. So then the cumulative GDD for those 2 days is basically combining those. And that can be done for the whole entire season. So this is a very good publication to look at if you're interested in how corn and other crops are managed. And that is really emphasizing that crops, of course, are affected by many number of factors: fertilization, rainfall, whether it's sunny or cloudy, hybrids, or even like maturity groups, whether it's a later maturing or early maturing varieties. But all of these factors are basically playing kind of a secondary role, because the temperature is still driving force behind the plant growth. So, in this case of corn, temperature is really what determines when a corn crop tassels or when it's ready to harvest. And so many years of observations have shown that plant development at any point time during the season is affected very predictably by how warm or cool the season has been to that point. And that is why that knowledge is really helpful to, to see if we need to make any in-season adjustments, maybe helping with supplemental irrigation, and also to predict the outcomes of the growing season in terms of yield. So the knowledge of climatic conditions can really help producers to better manage their crops. So for example, if a crop is slow in emergence or slowly emerging, then the producer could look, for example, at the GDD accumulated since the planting, from planting until now, and see whether that number was below 150, which typically would indicate slow emergence is probably due to like a cooler season, cooler soils. And if it's significantly more than 150 degrees GDD that have been accumulated, but the crop is still not emerging, then we can kind of confidently say that there might be something else is going on and some other problems such as low soil moisture, poor soil fertility, or disease should be looked at. So this is an example of long-term, in this case, it's 30-year average GDD accumulation for typical corn growing season at 3 different locations. You can see it's pretty close to the in trend, but definitely differs across those 3 locations. That is why our growing conditions and our yields vary drastically from field to field. So we talk about temperatures. However, that is just a part of issues or aspects of crop production that farmers are dealing with on a day-to-day basis. So it's really part of this integration production, and really a whole farm approach is what most growers turn into, because simply fixing in one area may not be, or almost never enough to be successful in terms of crop production. So they need to look at pest management, irrigation, the soil conditions, and choosing correct, appropriate hybrids, varieties. And then that temperature becomes just almost a small piece of this larger puzzle that growers are really needing to pay attention to. And then when we look even, if we zoom out even more, we know that this IPM and best management practices are really they are at the center of crop production, but again, a piece of a puzzle, because growers are dealing with consumers, they're dealing with marketing of their products, economic sustainability, environmental sustainability. So it is really kind of complicated, not just from the point of view of biological systems, but on a larger scale, because they're part of this economy. So it's very challenging. So in Virginia, for corn, for example, we know that the yields have been increased quite a bit, and that in part is due to improved practices and long-term research. In this case, for wheat as well. So sometime October, November is when we're planting winter crops. So we need to really pay attention to freezing events. And September to November is really when we have the risk of frost, plus minus a week. And we know that our growing conditions are very changeable from year to year. So, but basically the freeze events is what we need to be focusing on. And there's this very nice publication that summarizes growing wheat in the Mid-Atlantic region. It really talks a lot about planting dates. So for winter crop, sometimes we have producers that wanting to experiment on their farm, and they have questions on how late or how early we can plant a certain crop, in this case like winter wheat. And a lot of times it's just their timing of planting is dictated by the cropping system, what was planted before, what access to the field they had, what's going on with their equipment over the soil conditions at the time. But there's very important conditions that we need to look at, because planting too early, we have very warm soil. So then in that case, we have early emergence and development of those first shoots. And in that case, we have greater insect pressure and disease pressure. And because the plants are developed more than they should be really at that, the growth stage is more advanced than they should be. In that case, a lot of times wheat is not able to handle the winter temperatures, and that may result in a greater risk of winter injury. And of course, all of those things tend to reduce yield potential. So then in that case, when we plant in cooler soil, we actually help roots to develop faster rather than the above ground biomass. So then we have more extensive, more stable, better developed extensive root system, which actually helps to optimize our yields. Then if we plant too late, though, if we wait too late, we tend to have fewer tillers, and that means fewer heads or spikes. So that, of course, also reduces yield potential, because tillering, adequate tillering has been shown to be about, or being responsible of about 70% of grain yield. So the tillering stage is very important. That's why planting dates are very important to follow as a guideline. So this is the hardiness zone map that shows how planting dates could be affected by, and of course these are typical dates. So let's look for zone 7A, for example. It's pointing out the last spring frost to be sometime second, third week of April, and then the first fall frost is October 15 to 25. And you can see it varies quite a bit from location to location. So this indicates the average last spring frost and the first killing frost date for each of those hardiness zones. So this translates into kind of three major regions that have optimum planting dates as shown on the screen. And these are very good to follow for growers as a guideline. Again, within the cropping systems, a lot depends on farming practices and preference or experiences that growers have with their fields, with certain varieties that they like growing or maybe trying to start growing on their farm. And sometimes seeding rates, this we're talking about winter wheat, but for example, a lot of times corn hybrids come with prescribed seeding rates recommended for them, because as the breeders develop these new varieties or hybrids, they actually work on developing kind of sets of conditions at which that variety or hybrid performs the best. And seeding rate is something that sometimes plays an important role in optimizing yield potential. So there's a lot of research has been done, in particular looking at different varieties of wheat, planting time, and combination with different seeding rates. And you can see that there's recommendations based on planting time and row wheat in inches, and then it depends on like I said before, a lot of times growers just unable to enter the field and plant within a certain time that they typically would like to. So there's certain things that could be done to still push the yield, such as maybe increasing seeding rate. However, it's not really always resulting in, optimized yield, because the growing conditions just won't allow for that. So here's an example of plants seeded at the same time, but at different seeding rates. So you can see that the response of crop is really varied, and not just temperatures, but also interplant competition can affect your results. And of course, the seed size somewhat tied with the seed population or plant population or seeding rate. So that's something that should be also paid attention to. So this is the same number of seeds, but seeds are different size. So you can see that really when we're determining the plant population, a lot of times it's not just the number of seeds, but it also quality of seeds that affects it. Moving to the fertilization and nutrient management for wheat. So what really growers are striving for, and what's recommended, what would be the ideal situation, is we could really spoon feed every single plant in that field. there's already technology available that allows to evaluate every single plant, every single corn plant at least, and spoon feed that crop according to yield potential of every single plant. Of course, it's not yet something that any grower is able to do in their plant in their fields. But the idea is basically now what's the next best scenario? We're still trying to provide enough nutrients at the right time and the right form, um, where the plants can really take up the nutrients as needed, and the that would really decrease the loss to the environment. So in terms of wheat, about 60% of nitrogen uptake, which nitrogen is one of the most limiting nutrients, happens after Ficus 5, which is tillering stage. So that means that we're trying to really apply nutrients around that time. A lot of times our soils already contain sufficient amount of most nutrients or all nutrients, depending on the field. Of course, that's why soil testing is so important. To know what's in the soil, what kind of residual soil nutrients we have from the previous harvest. But a lot of times we do have enough to get the planted crop through the first initial few weeks. However, of course, it needs to be verified. But then in case of wheat, Ficus 5, when this is extensive growth occurs, and this is very active growth and development of both roots and the biomass, tiller creation. So this is very important to make sure that we have sufficient number of, amount of nutrients during that time available to the plant. It has been shown typically that split apply nitrogen according to growth stage, which kind of what I mentioned earlier, spoon feeding, but not as extensive because we're just splitting nitrogen instead of applying everything at the time of planting. We're splitting between pre-plant application and then in-season nutrient management. So typically that shows better results, especially in soils that tend to have a lot of leaching, or like super sandy soils that have a lot of percolation happening, or if we have extensive rainfall that our crop can just lose nutrients before they even have a chance to start taking it up. So split up application of nitrogen and most of mobile nutrients such as sulfur as well is recommended. However, it's not really always true. A lot of times, we see in trials and in just from grower reports that all nitrogen was applied pre-plant and the yields were not different from split application. However, those are typically years when the growing conditions overall are very mild, very beneficial. But like I said, if we have some extensive rainfall or cooler temperatures, and for example, wind, if urea was applied, for example, on the surface of the soil, we can have up to 80% loss of that nutrient before plants ever start taking it up. And so this shows nitrogen rate is directly related to tiller numbers. So very important, again, the tillering is a critical growth stage for wheat. And that is why the recommendations are typically tied to tillering. So this is what the plant looks like around Ficus 5, 6, which is just prior to start initiation of jointing. and this is active tiller creation. And this is the time when most fertilizer applications are done in the field. And not only it's related to tiller number, but also directly related to the nitrogen rate, directly related to tissue nitrogen content, or the content of nitrogen in the leaves in the above ground biomass. So you can see that really recommendations have to be tailored to our growing conditions, and can dictate the outcome of the plant performance. So for fall management for winter crop, we normally, for fertilization, we normally do just down to 6 inches with soil nitrate tests are tested. Levels are tested down to 6 inches, and that's because, of course, later on, wheat roots develop much deeper, and they will reach, sometime up to 4 feet, depending on the soil and the variety and growing conditions. But at the beginning of the season, we're just wanting to have enough to start that growth going, and to stimulate the emergence, stimulate those first tillers being formed, and mainly the roots. So normally, if we have less than 10 ppm of soil nitrate within the first top 6 inches, um, we may see some nitrogen deficiency symptoms in seedlings. So that is why I'm saying that soil testing annually is very, very important. Sometimes it's difficult to justify from economic perspective. However, just one good soil sample per field, a composite sample, can tell us a lot about general condition, and it's still better to invest rather than not test at all and hope that we have enough in the soil, or waste resources potentially applying some nitrogen where we don't really need it. So less than 10 ppm, we typically would see the nitrogen deficiency symptoms in seedlings. So then we would recommend applying up to 30 pounds. Typically, for our small plot research, we usually apply about 20 pounds of nitrogen at planting or right before planting to get those roots established. And then if we have anywhere between 30 and more, then that indicates really that we have sufficient or adequate amount of nitrogen in the soil already. So we wouldn't recommend any nitrogen at the time, because that would be enough to really initiate plant growth. And then the spring nitrogen management is also very important, because that's when we're really targeting optimizing yield and quality. And so the spring nitrogen application often produce higher yields that can be produced with any rate or timing in one single application. So that's why split spring applications typically better and produce higher yields. And there's a diagram that shows, based on tiller count early in spring, whether nitrogen fertilizer is needed or not. And then, depending on the grower situation, whether they're willing to invest in splitting the fertilizer, then they can do a soil test, or do even a tissue test to determine the amount of nitrogen needed. And that is tied also with a lot of things, but from economics point of view, of course, at the moment and for a while now, growers are struggling financially. A lot of wheat growers right now are actually in the red when they are managing a wheat crop, even when their yields and quality is good, because of relatively low price of grain at the moment, and fertilizer costs are still pretty high. So of course, all of these things and decisions are made, on a daily basis by growers. But this is the ideal situation we're talking about. What could be done to improve crop growth. Okay, so this is what I had for crop production for you today. If you have any questions, be happy to answer. Or you can follow up later with me.
I didn't see anything in the chat yet, but
Okay,
sometimes people come up with some things.
yeah,
We're a little ahead of schedule, which is never a bad thing. So why don't we take a break now? And we'll be back at 2:45.
okay.
And if anyone
Done.
thinks of any questions between now and then, drop them in the chat, ask them when we get back. Happy to answer them.
Yeah, thank you.